Good morning, students. Welcome to the class on NMR Spectroscopy. Today we will discuss some advanced topics on NMR Spectroscopy. First, we will look at the coupling constant values. Please take the notes. Carbon-proton coupling constants generally vary from 110 to 270 Hz. In this, sp3 Yep, all of you please mute yourself. In this sp3 carbon hydrogen coupling will be between 115 to 125 Hz, whereas sp2 carbon hydrogen coupling constant will be 150 to 170 Hz, and sp hybridized carbon hydrogen coupling constant will be 240 to 270 Hz. And I'll try to give other coupling constant values also. Carbon fluorine coupling constant will be between 165 to 370 Hz. 165 to 370 Hz. Carbon phosphorus coupling constant will be 45 to 56 Hz, and it will be even more in the case of the coupling constant value depends on hybridization of phosphorus. Please remember the values from previous class. Carbon 13 deuterium coupling constant will be around 20 to 30 Hz. 20 to 30 Hz. Phosphorus and proton coupling constants will be 190 to phosphorus and proton coupling constants will be 190 to 700 Hz. Now we will look at geminal coupling constants. That is 2J, two bond coupling. Generally for this geminal coupling, the coupling constant will be from -9 to -15 Hz. For this geminal coupling, it will be 0 to 2 Hz. For carbon, for hydrogen and deuterium, geminal coupling will be around 2 Hz. Fluorine, geminal coupling will be around 160 Hz. Hydrogen fluorine geminal coupling will be around 50 Hz. Hydrogen carbon coupling geminal coupling will be around 5 Hz. Hydrogen and phosphorus geminal coupling will be 7 to 14 Hz. Now we will look at 3-bond coupling. 3-bond coupling between these two protons will be 0 to 2 Hz. 3-bond coupling between these two protons will be 2 to 4 hedges. Similarly, 3-bond coupling here will be 5 to 7 hedges. For a 6-membered system, the 3-bond coupling will be 8 to 11 hedges. For simple alkene, this 3-bond coupling, which is nothing but cis coupling, it is 6 to 15 hedges. So this is cis, 6 to 15 hedges. Trans 11 to 18 hedges. Cis coupling between proton and fluorine is 18 hedges. Cis coupling between proton and fluorine will be 18 hedges. Trans coupling between proton and fluorine will be 40 hedges. Cis coupling between fluorine and fluorine will be 30 to 40 hedges, whereas trans coupling between fluorine and fluorine will be 120 hedges. We also have long range coupling, that is 4-bond coupling. Long range coupling values are generally very small. Sometimes they are even 0 also. So that is why we generally don't worry about the long range couplings. But yeah, precisely long range coupling do exist. For example, long range coupling between an allylic hydrogen, this is an allylic hydrogen, A, B, C. So an allylic hydrogen HAC, HBC is generally between 0 to 3 hedges. Coupling between A and C hydrogens or B and C hydrogens is generally between 0 to 3 hedges. We also have W coupling. For example, in this molecule, when we look at these two hydrogens, they are related to each other through a W bond. So it is called W coupling. W coupling is also very less. Generally, it is 0 to 1 hedges. W coupling is also very less. W coupling also exists in bridged bicyclic system, but with a different hydrogens. Now look at these two hydrogens. These two are also having W coupling. So here the W coupling is 7 hedges. Here the W coupling is 7 hedges. Please take this correction. This is only one carbon here, not 2 carbons. Okay, I'll redraw this. The W coupling between these two protons is 7 hedges. We know chemically equivalent protons. In a similar fashion, magnetically equivalent protons will also exist. Now we will look at this concept. What are chemically equivalent and what is magnetically equivalent? When we take an element of symmetry, for example, in this case, a plane of symmetry. When we take a plane of symmetry, a plane of symmetry exists in this molecule. So these two are mirror images to each other. So that means when a plane of symmetry exists, then these two carbons or these two methyl groups are chemically equivalent. Chemically equivalent. As we know, chemically equivalent protons will give only one signal and they never split each other. So how many signals we expect here? We expect only one signal in both the proton NMR as well as carbon NMR, and we don't expect any splitting. Right. I'll give you one more example where we will have axis of symmetry. Now look at this molecule, Sahar's projection anti. We can go for an axis of symmetry C2, axis of symmetry. When we do axis of symmetry, this chlorine will occupy this place, this chlorine will occupy this place. So when we have an axis of symmetry, then also we will say these two are chemically equivalent. These two are chemically equivalent. So how many signals we get? We get signals for the protons on this carbon only. Because these two are chemically equivalent, we get only one signal. And these two hydrogens are also chemically equivalent, so we get one signal. We get one signal both in proton NMR as well as carbon NMR. Now look at this example. This is fumaric acid. When we look at this example, again we can go for an axis of symmetry C2. Axis of symmetry. Take an axis C2 in perpendicular direction to the plane. So when we rotate, this carboxylic acid will occupy this place, this carboxylic acid will occupy this place. So as a result, we can say fumaric acid, the two carbons are chemically equivalent. Chemically equivalent. So how many signals we get? We get only one signal for these two protons. And because they are chemically equivalent, we don't expect any splitting here. We don't expect any splitting here. Okay? Right. Even carbons also, we get one signal for this carbon, we get one more signal for this carbon. So we get one signal for proton, two signal for carbon 13. Two signals for carbon 13. Now I will give you two more examples. You try whether there is any symmetry element or not in these molecules and how many signals do we expect for these molecules. Now just look at the symmetry elements and tell me about the possible proton and carbon signals. So in this molecule, we expect a C2, a rotational axis. So as a result, these two carbons are equivalent. At the same time, these two carbons are also equivalent. So we expect two signals for this proton and the protons and methyl group. In proton NMR, we expect three signals in carbon 13. One carbon, second carbon, and the carbonyl carbon. So we expect two signals in proton NMR, three signals in carbon 13 NMR. Here we expect plane of symmetry. Plane of symmetry. like this. So when there is a plane of symmetry, these two carbons are chemically equivalent, these two carbons are chemically equivalent. So we get only two signals, proton on this carbon and the protons on this methyl carbon. Therefore, this type of protons are called as chemically equivalent protons. So this nuclei itself, they are called chemically equivalent. Because they are chemically equivalent, they exhibit same delta values and they do not split each other. They do not split each other. Chemically equivalent protons are also called as magnetically equivalent. Chemically equivalent protons are also called as magnetically equivalent. Now we will look at an example where the protons are chemically equivalent but magnetically non-equivalent. Take this example, a para disubstituted benzene with two different substituents. We have two protons on the right side and two more protons on the left side. In general, the HA and HA, these two protons look like chemically equivalent because they are ortho to X. HB and HB, they look like chemically equivalent, right? But how they are magnetically equivalent? So to differentiate them, I'll give a prime, HA dash, HB dash. Right. As we said, these two are chemically equivalent. They are magnetically equivalent. These two are chemically non-equivalent. Chemically non-equivalent. So they will split each other. We will observe a 3-bond coupling here. A 3-bond coupling here. When we say chemically non-equivalent, we can also say magnetically non-equivalent. Similarly, HA and HB, HA and HB, they are magnetically non-equivalent. Magnetically non-equivalent. What are magnetically non-equivalent? Magnetically non-equivalent look like chemically equivalent, but they will have different coupling with different atoms. They will have different coupling with different atoms. For example, coupling between these two is different. Coupling between these two protons is different. I'll give a very simple example compared to this, where we can easily observe chemically equivalent and magnetically non-equivalent. These are chemically equivalent, magnetically non-equivalent. Right. Look at these two protons. Now consider HA proton or HB proton. HB proton, it is cis related to this fluorine, whereas it is trans related to this fluorine. So we observe two different couplings, right? Here there is a possibility for plane of symmetry. That means these two protons are chemically equivalent, right? But they are magnetically non-equivalent. Though we expect a plane of symmetry here, these two protons are magnetically non-equivalent. Here they will exhibit two different couplings. one type of coupling with cis, another type of coupling with the trans. Similarly, the fluorines also magnetically non-equivalent. The fluorines also magnetically non-equivalent because they expect different couplings with the different protons. Okay, so this Hb is having cis coupling here, trans coupling here. So that means this proton is not magnetically equivalent. Now we look at homotopic groups. What are homotopic groups? Homotopic, enantiotopic, and diastereotopic. These words are from stereochemistry. So when we have homotopic groups, they are always chemically equivalent, isochronous. So they don't split each other. They will give only single NMR absorption. They will give only one peak. Homotopic groups are interchangeable by rotational axis. So when we operate a rotational axis, these homotopic groups are interchangeable. Now I will give some examples for homotopic groups. Look at these two protons, HA and HB. When we have same substituents, both X and X, then it is not a chiral center because these two substituents are same. Even if we replace HA with some other element, say for example, I am replacing it with some other element A, now also it doesn't become chiral. Now also it doesn't become chiral. These type of systems are called homotopic. If I replace B with some other element, then also it doesn't become chiral because these two are same. Okay, so these type of systems are called homotopic. This type of protons, these two protons are called homotopic. So when we have homotopic protons, they will give only one signal because both are identical. Both are identical and they did not give any chiral center. Both are identical, so they give only one signal. These two protons will give only one signal and they don't split each other. I'll give one more example for this. Look at this molecule. Now look at these two methyl groups. On this carbon, these two methyl groups, they have same substituents. Say for example, in this case, X and X. So these two carbons are X and X. Because these two are same, even if we replace one of the methyl with some other group, then also it doesn't become chiral. If it doesn't become chiral, then what we can say, these two are homotopic. So these two methyls are homotopic groups. So these two methyl, I'm not talking about these protons, okay? These two methyls are homotopic. So they give only one signal in the proton NMR. Similarly, in the carbon NMR also, these two methyl groups will give only one signal. So these methyl groups, one signal, they will give only one signal both in proton NMR as well as carbon 13 NMR. Why? Because these two are homotopic methyl groups.